So hello everyone, and my talk will emphasize a few steps which will you need to build your own front end from scratch. So the motivation for this talk is rather simple. We have a kaleidoscope tutorial which gives you some outline how one can build, for example, the JIT compiler for your own language and so on. But we don't have any extensible documentation about the backend building, especially from scratch. So from time to time, we have some questions in the mailing list, say, hey, how I can build a backend for my toaster? And unfortunately, we cannot answer, nothing new than look into the Spark or mix backends, and then maybe you will have idea how to do that. And this scares people. Here is the outline. First of all, I will tell a few words about code-gen phases and different parts of that. Then I will introduce our example target for this talk. Then there will be a few first steps which will everyone need to build a backend from scratch. So unfortunately, they are a little bit complicated, and that's why it's really necessary to emphasize them. Then I will show some example of more complicated thing that's dealing with something which is not supported for the given target. And then also there will be some outline of next steps. So, LLVM has pretty complex code gen. But fortunately, it can be separated into the few different phases. So first of all, I would like to mention that LLVM code generator uses its own IR called selection DAG, which is quite unique, and it's even more lower level than LLVM IR itself. So first phase of the code gen is preparation phase, when just LLVM IR is transformed to make a life of code generator a little bit easy. Then there will be so-called selection DAG phases, which does all that lowering to that internal representation of the code generator. Also then a few late optimizations are run on top of that IR called selection DAG. Then magic happens and we have a register allocated. Then several phases which are done after register allocation. And the last phases are code emission. So either assembler printing or binary code emission for the JIT and so on. Well, so the first two huge phases are selection DAG phases. So basically, there are 6 phases here. So the first phase is then LLVM IR is lowered to that selection DAG stuff. And then after that, some optimizations are run on top of that selection DAGs just to eliminate some, for example, common sub-expressions, to rearrange things, to canonicalize things, and so on. Then there is a legalized phase where everything unsupported by the given architecture is converted to some simpler forms. For example, consider you have some small CPU which does not support that 64 bits addition and so on, which will need to be split up into different parts and so on. Then we have another phase of combining. So because the legalization phase may emit a decent amount of the code. Then we have instruction selection and instruction scheduling. I will not go into details here because on the previous developers meeting, Dan had given, brilliant talk about that, so check it out. Next huge phase is the register allocator, which just grabs the selection DAG IR with all virtual registers in it and assigns the physical registers to that. So it's just a magic. And today we will have, Lang will give a talk about the register allocator. That's why I also skip it here. After register allocation, some phases are run. Most notable is the prologue-epilogue insertion and abstract frame indices elimination. So when the abstract reference to the stack frame objects are turned into the real stack manipulation stuff and so on. When there is a possibility to run the post-register allocator schedule, because the register allocation and prologue-epilogue insertion might emit stuff like spills and so on, and that's why sometimes we need to rearrange the things to get a better code. Then we will have when we have a branch folding path, which just tries to make as much branches to be just fall through as possible. So this is sometimes it's a really necessary thing. And also some late target-specific passes are run. For example, that's some IT block formation on some TWA2, delayed slot filler on Spark, and so on. There are many passes depending on the target we are using. So what is the LLVM backend itself? LLVM backend itself is just a standalone library which are hooked into the LLVM system, registered via different things, so hooked into the build system, and so on. Basically, it's written into the C++, and different parts are written in the TableGen language. TableGen language is a special domain-specific language which is used to just to describe different things in the simpler way. For example, register sets, register classes, allocation order, calling conventions, instruction patterns to select instructions out of selection decks, sub-target features, and many, many other things. Then this description in the TableGen language is then just pushed to the special tool which emits just plain C++, and then we have just a C++ library at all. Also, the LLVM code generator is pretty target neutral, and that's why inheritance and overloading is used to, well, to hook necessary target-specific stuff into the LLVM code generator. So here is the example of different parts typical backend consists of. First of all, we have So first of all, we have two classes, it's subtarget and target, which describes our target and provides some necessary information about different flavors of target and so on. We have a special class for the lowering. Another place is that we have a description of the register sets and register information. And then we have a description of instructions. So note that these files also has some TableGen descriptions. Also, we have a separate class to help the instruction selection. We have calling convention description into the TableGen files. Also different things for assembler printing, JIT emission, and many other things. Here is our example target. So basically, I just selected this small 16-bit RISC-based microcontroller unit for the demonstration here because it's rather small, it's rather simple. So for example, it has only 27 instructions. But basically, you can apply everything which can be shown here to your favorite, for example, soft-core processor, something like, well, PowerBlaze, MicroBlaze on Xilinx and so on. So we have 8 or 16-bit data. We have 16-bit pointers on this processor. It has some powerful addressing modes. As I already said, it has just 27 instructions. And also, most of instructions are available in 8-bit and 16-bit variants. So, and we are going to build something easy for this microcontroller unit. Here is our first example. Consider you have this small LLVM IR. So pretty complicated one, but that's the one which everyone should start from. So so how much we must code to let this thing even to be compiled? Unfortunately, a lot. Yeah. And the first few steps are a little bit complicated. That's why it scares people. But after these steps will be completed, then everything will be more or less straightforward. So that's why these first steps needs to be implemented. First of all, one should write some skeleton backend. So one should just provide a blank backend classes. One should provide the data layout for the given target, so describing that all different stuff like the sizes of pointers, alignments, store size for different types, and so on. So it's pretty straightforward, but it needs to be done. Also, it's good at this stage to describe the register set for given target. So just given the sets of, well, for native types. In our case, it's 8 and 16 bits. Yeah. Surely, one can proceed without this step and then add the register classes later, but it's good to have them at this point, because it will allow to have well, just cleaner code in the beginning. Then all this should be just hooked into the build system and registered in different places and so on. After that, one should actually describe the calling convention used for the target, because everyone you have is the function. Function has input arguments, it has return values, and so on. That's why one needs to describe the calling convention used for the target. It's pretty straightforward in most cases. So one just needs to write a small table gen code. Yeah, here's an example. So one should just tell which arguments, how they are passed, so on stack, on the registers, and so on. And then magic happens, and table gen tool will just from this description emit C++ code, which will later use to recognize the incoming arguments, and most of bookkeeping code will also generate it. So it's rather easy. The next step is not as easy. One needs to implement custom lowering for the formal arguments and for the return value. And this is the first thing need to be done, and it's not as easy. So it's better to look, for example, into the one of existing backend just to read the implementation there and try to figure out what's happening there. Yeah, so basically for the return, we also need a return instruction. So we need to provide a target node for that, a selection deck node. And we need to add an instruction selection pattern for this node. Here is what should be done into that lower formal arguments method. Basically, one should assign the locations to all incoming arguments. So they're coming into either in the registers or on the stack, depending on the target. Maybe they're coming splitted and so on. At this point, basically, that calling convention description is used just to get the precise location of the input arguments. Then they are loaded into the virtual registers, or for example, for the arguments which are passed on stack, we have that abstract frame indexes stuff, and we need to load out of that frame object. Yeah. And actually, the same sequence of actions for the lower return routine, but into the reverse direction. So we need to assign the output registers, we need to put the stuff on stack if we need, and so on. After that, we need to provide some information for the backend. Basically, we need to provide a few hooks into that register info.cpp file. We need to provide a set of reserved registers. The reserved registers are the registers which will never be allocated by the compiler. For example, that status flag registers may be the stack pointer, the instruction pointers, and so on. So that's just not ordinary registers. Also, we need to provide some small hook telling whether we are using or not frame point elimination. One can, at this stage, leave it blank and return true or false. We also need to provide a set of callee-saved registers and the register classes, so depending on maybe sub-target or all different things. At this point, we will need to add the functions to emit a prelogue and epilogue for the function, but just leave them blank for a while. And the last, we need to add some instruction printing skeleton for the assembler mission. That's not that hard, because almost all assembler printing is auto-generated from the instruction description. So one just needs to do things like, well, get the string out of a generated part and move it into the output stream. So it's also straightforward. And after that, we have a nice output out of LLC tool. But actually, we implemented more, since we have a more or less full description of the calling convention. That's why let's try to generate code for something more complex. Either try to return some value here, or return stuff coming into some register. So we have two variants here. In order to support these things, we need to implement moves. First move is actually load the immediate into the register. Here is an example how the pattern into the .td file looks like. So we have a set of input arguments, so it's just the immediate. We have the output register. We have templatized assembly output string, and we have actually a pattern which will be used for the instruction selector to match some things into the DAG. And also here we add some hints for the code generator. After adding this, we will be able to get this nice output. Note that we haven't implemented any epilogue emission code, and we also have only skeleton implementation of the assembler printer. That's why the output here looks pretty simple. So we don't have any crazy things like declaring what function is and so on. Next thing is register move. Basically, there is no way to match register moves inside the DAG, inside the selection DAGs. That's because the register moves are just emitted by the backend itself. That's why they need to implement a hook which will just add the instruction which move one register to another. Also, at this point, it's nice to have another routine which will just recognize the moves. This is used, for example, for redundant moves elimination and so on for the backend. And we need to provide just definition for this instruction. So we have register as input, register as output. We have assembler string here. So pretty straightforward. And here what we have. So I just extended the example. So we don't have a redundant move just for the same input argument to the same output argument. So we have just move from one register to another. And at this stage, we have everything ready for the simple arithmetics, which will either use both register arguments or the immediate arguments. One just needs to add some set of instruction patterns for that. So here is the example for the addition which are made into the registers. So basically, we have two input registers. We have one output register. We have that matching code. Also, we have some hint that this instruction actually alters the processor flags, so it sets carry flag if needed. So that's why they shown that it has that status register defined and also have that implicit defined for that. And we add few hints for the instruction selector. So we tell that that the arguments of this instruction can be commuted. And also it's two address instruction. That means that one of the input operands is tied to the output operand. Yeah. Here is the example of the code emitted here. The same can be added for the subtraction, for the addition with the immediate, for all logical operations, and so on. Our MSP 430 microcontroller unit has a quite small instruction set, and it even don't have a 2-bit shift. We only have a single-bit shift here. That's why we need to do something, well, not so straightforward to support this small code, which is just arithmetic shift right with 2 bits. Yeah, we need to custom load the shift to the target-specific single-bit one. Here is the way how this can be done. So basically, we need to mark the shift operation as custom lowered. We need to add the new target node for the single-bit shift. Then we need to add code to expand the series of single-bit shifts to expand the multi-bit shift into a series of single-bit ones. We need to declare a new target node into that instruction info.td file and add an instruction pattern which will match that special node and emit just a single-bit shift. So Also, at this stage, we can insert some optimizations. For example, if we have a quite huge shift, we can do a trick having so just doing the swapping the bytes, then doing sign extend, and then remove the shift by 8 this way. It's much cheaper. Yeah, and here is the example output from the code generator. So we have just 2 nice shifts here. What should be done next after we completed that steps? First thing needs to be done is the memory operands. So you need to add a custom instruction selector logic for the selecting all different addressing modes and so on. Then we need to add descent, prologue, epilogue emission code and the code to support all stack frame handling things. We need to handle the call is saved registers, so we need to emit sequences of operations to spill them to stack and to reload them if necessary and so on. Also, we have some huge amount of different instructions to support, namely comparisons, jumps, calls, globals, dynamic allocations, jump tables, well, some other arithmetics like multiplications, divisions, and so on. Also, it's good at this point to write a small snippet of code and to hook our newly built backend into Clang. That's why you get the C front end almost for free. So it's only a matter of a few kilobytes of code to hook this backend into Clang. One should just describe different, for example, type sizes and nothing more. And also this stage, some target-specific optimizations can be added. So here is the conclusion. So one can build backend in pretty straightforward way. Well, surely given that your CPU is more or less sane. Building for the complex CPUs can be not so easy thing, but in any case, it's doable. Here is how one can proceed. So we have 2 backends which were built specifically in the step-by-step manner. And that's why into that commits mailing list, you have all that history starting from the skeleton backend until to that current stage. So here is the MSP 430 backend, and also that system Z, that's for IBM mainframes backend. There are some feature tests which can be used to cover all interesting instructions. So they can be found into that 2 different directories. If you need to handle something more complex, well, maybe some complex addressing modes or different things also, you can look into that huge backends like x86 or ARM backends, which are implemented many scary things. Yeah, and also the code from this talk will be available soon. So you can just look at that and have some idea what's happening. Yeah. I'm all.